So we are going to discuss problem number 66 and further problems in the quantum mechanics. As we know, you know that we have already discussed more than 60 problems or almost 65 problems, uploading 13 videos, which are very much helpful for people preparing for all sorts of entrance exam related to physics, or even to anyone who wants to pursue quantum mechanics. Can find helpful. Now, so let us start with this problem number 66, which says that for the case n equals to 2, l equals to 1, ml equals to 0, the value of r at which the radial probability density of the hydrogen atom radius reaches its maximum is what? So the question is asked that you have some values given for n equals to 2, l equals to 1, and ml equals to 1. So these are the quantum numbers, you know, right? Principal quantum number, azimuthal quantum number, and magnetic quantum number. Now, these represent some wave function and certain state and corresponding wave function, right? So it is asked that what is the radial probability density. Now it is important to understand. First, what is the probability density? You know that it is psi star psi, right? The wave function is square and integrated over the entire volume. Now here, it's a probability. And here probability density is, if you are not integrating, only taking the density part, right? So here radial probability density is basically defined as this is a general formula which says that radial probability density PR, if you denoted by PR, where P is the probability density and R is obviously the function of R, it's nothing but it is a function of R square, where R is square the radii, and then the probability density function is a probability function square, right? So R square is there, and then your wave function, which is given right here, right? Remember that it is a probability density, so it is not integrated over the volume. So now it is asked that at what value it is maximum. Now you know that the maximum minimum condition from mathematics, any function, if it has to be maximum or minimum, its first derivative must be equal to 0, right? So ddr of PR is equals to 0, right? So total derivatives, so it means, it says, just put R here, so it will be, what is this R square, and this is 1 upon 2 A0 whole cube, and R square A0 square into 3 into exponential of minus R by A0, right? So just multiply, it gives you what? It gives you differential of nothing but this function, which is R to the power 4 and 1 upon 8 A0 cube and A to the power A0 to the power 5, right? Into 3, obviously 3 multiplied by A into A0 cube into A0 square into e to the power minus of R by A0. Now this is a simple differentiation, right? So just differentiate it. So it will be giving you 4R cube divided by 24 E0 to the power 5 e to the power minus R by A0, right? Minus differentiation of What is differentiation of e to the power minus r by a? You know that e to the power ax is nothing but a e to the power ax, right? So it is minus of 1 by a e to the power minus r by a naught, right? So just equate it to 0. As exponential term is not going to be 0, right? It means it gives you what? It gives you, you take r cube common and divide it. This 6. So you take common, or basically you take leave it. You take 1 upon 24 a naught to the power 5 common, and then this term r cube h common, giving you 4 and e to the power minus r a naught. 4 minus r, so it is plus r by a naught is 0. So r is nothing but, right? So here it is not minus basically, it is plus, so here it is minus. Right? So r is nothing but 4a naught. So this is your equilibrium radii, r equals to 4a naught. Right? As other terms are not going to be 0. Right? So this is the answer. So maximum, it is maximum at r equals to 4a naught, this probability density. Right? So this is a simple but very important question, and it is radial probability density is frequently asked, and sometimes probability is also asked. So if you remember this, that radial probability density is nothing but the probability density, wave function of the radial part of the wave function multiplied by the r square. You are not adding dr here, as you are taking only probability density. Remember that. Right? This is one simple question which is very significant. Please note it down and try to solve similar problems, as they may arrive in any of the question competitive exam. Now let us take this problem number 67, which is very much significant, and it is based on the Heisenberg's picture. It says that the Hamiltonian of a system is given by ht equals to p square by 2m plus v rt. The Heisenberg equation of motion for the position operator rt in the Heisenberg picture for this system can be written as what? Right? So this is a question mark. We need to find the equation of motion for the position operator in Heisenberg's picture. Right? So let us try to understand how we can address this problem. Now, as you recall, the Heisenberg picture says that for an operator dA, its total derivative dA by dt equals to nothing but 1 by I h cut times a cap comma h cap, where a and h are h is Hamiltonian operator and a is the operator whose time evolution we are calculating, plus del a cap by del t. Right? This is called the Heisenberg's equation of motion. Right? So now, as we are dealing with a position operator, let us try to write its equation of motion dr by dt, which is equals to 1 upon I h cut and r h cap plus del r by del t. But remember that this term only survives when the operator explicitly depends on time. But here it doesn't explicitly depends on time, so we are equating it to 0. So it will vanish obviously. Now let us calculate this commutator. It says that 1 upon I h cut r and then P square by 2m plus Br. Right? Now it will have two commutators. What are those? It will be R cap P square by 2m plus R cap Br. Right? Now remember that commutator of two operators which depends on the same observable is vanishing. Right? So this depends on the same observable, that's why it's a vanishing. Now you are left with this one, which is you can use the formula. So it will be what? It is nothing but np to the power n minus 1. Right? So it gives you 1 upon I h cut into 2p divided by 2m into r comma p, which is nothing but I h cut. Right? So I h cut, it gives you 1 upon I h cut into I h cut into p by m, cancelling out I h cut. So you are left with dr by dt as p by m. Right? So this is your equation of motion. Simple equation of motion. This is this type of questions are very frequently asked in NET and GATE type of exams, or even the PhD entrance exam. Right? So hope you will find it useful. Let's write it down. Now let us take this problem which says that find the degeneracy of first excited state of hydrogen atom when spin is included. Right? A very important problem. As degeneracy is very frequently asked. Right? So the degeneracy of hydrogen atom in the nth state is defined as summation over L equals to 0 to N minus 1 2L plus 1 multiplied by 2, where 2 is obviously for the spin part. If a spin is not there, then only this part is without a spin, right? And this part is with a spin. So just add it. So you will find that for L equals to 0 it will be 1 and it will form a series. Right? So it will be 1, 3, right? L equals to 0, it is 1, L equals to 1, it is 2 multiplied by 1 plus 1 is 3, for L equals to 2 it is 5, plus 7, plus dot. Right? Up to n minus 1. So 2 into n minus 1 is 2n minus 2 plus 1. Right? 2n minus 2 plus 1 is nothing but 2n minus 1. Up to 2n minus 1. Right? So just if you are, there is a simple progression. If you will add it, you will find the summation as n square. And then this 2 multiplied by this. Right? So it gives you the degeneracy of nth state is nothing but 2n square. So degeneracy of the first excited state is, which is nothing but the second state, is nothing but first excited state is 2 times 2 square, which is 8. Right? Very important result. Hope you will always remember it. And it can be asked anywhere in the exam. Right? Now let us discuss this problem number 65, which says that a particle of mass m and charge q is moving under the influence of a one-dimensional harmonic oscillator potential. Assume that it is placed in a constant electric field epsilon or E, and the Hamiltonian is given by h equals to p square by 2m plus half m over square x square minus q epsilon x. To write then write the energy of the nth excited state, right? So let us energy of this excited state is nothing but the expectation value of Hamiltonian, right? So how we can calculate it? The expectation value of Hamiltonian, as we do not have any wave function, right? So let us first change this, modify this, right? En, right? So now we are modifying Hamiltonian by writing it in this fashion. Right? Now how we are writing? We are defining that y equals to x cap minus q epsilon divided by m omega square. Right? So if you put it and change it, you can check that this is what we are getting. It will be giving x square plus q square epsilon square by m square omega square, right? Now remember that you are taking half m omega square common here, right? And when you will expand it, you will find this term, right? It is coming from this only. So we are just changing it and adding and subtracting by adding and subtracting this term, right? So just check it if you have any doubt. Now, if you calculate the expectation value of this, it will get it is nothing but the h naught of the usual harmonic oscillator. So its expectation value is nothing but m plus half h cut omega, where omega is the frequency of the oscillator, and this term, which is nothing but a constant term, will be simply added. It acts like a constant perturbation term. So Hamiltonian will be nothing but m plus half h cut omega minus q square epsilon square divided by 2m omega square. Right? A simple but very significant problem. Remember that this modification, changing it into the x square potential form. And removing x, right? Problem number 70, which is very important. It says that the expectation value of physical observable O in Schrodinger's representation is same as the expectation value of Heisenberg's representation psi OH psi, right? So this statement, remember that it is a true statement. So these two representations, the Schrodinger and Heisenberg representation, are equal. They are just two different methods to solve the same problem, right? So they do not differ. So their end result do not differ. So expectation value remains same whether you choose Schrodinger's picture or you choose Heisenberg's picture, right? So never get confused about that. Always remember that it is end result of Schrodinger and Heisenberg picture is same, right? They both give same expectation value. So this is all we have in today's lecture. We'll come up with more number of problems on the different advanced topics in upcoming lectures. So please stay connected.